Good afternoon to everyone. For those of you who don't know me, my name is Gabriele Guerini and I'm an assistant professor with the Department of Civil Engineering and Architecture at the University of Pavia in Italy. Today, my presentation will be about some innovative strengthening solutions for existing masonry buildings. Now, this slide, I guess, is already familiar with those of you who have followed the previous sessions of this webinar series. This is the framework of the Eurocode 8 Part 3 for existing buildings. And with today's webinar, we are going to focus on the last point in the framework, which is the design of the necessary retrofit interventions if a building is deficitary after the analysis in the current state. Now, let's recall very quickly how a masonry building may fail, the main failure modes for this kind of buildings. First problem is the quality of the masonry. If the masonry is really poor in terms of mortar, strength, blocks, stones, shape of the blocks of the stones and their interconnection, well, we may have failure of the material itself. If we don't have this problem, a second level is the one related to connections, because we may have out-of-plane collapses of portions of walls because of poor interconnections with the intersecting walls or with the diaphragms. And only if we solve these two problems, or if these two problems are not present in our building, we may have a global response of the structure where the elements respond in their planes, where elements are piers and spandrels of the walls. And in this case, we can take advantage of most of the strength offered by the masonry. We would ideally be in this condition, and in some cases, it may be necessary to strengthen our elements, our piers, our spandrels for the performance in the plane. And this is what we are going to see mainly today. Now, even if we provide good connections between intersecting walls and between walls and diaphragms, we may still develop some local mechanisms. In the previous webinar, we saw some techniques for improving these connections. But even in this case, we may see especially vertical arching of the masonry walls out of plane between floors, especially if we have opening alignments, if we have not so good connection with intersecting walls, and if we have poorly interconnected masonry leaves within the wall. But mostly, in the case of good interconnection between elements and between walls and diaphragms, we may develop mechanisms in the plane of the walls, which may be classified in two main families: spandrel mechanisms, where spandrels are cracking and getting damaged, while piers are not significantly damaged, if not at the base, because of bending; or sub-story mechanisms, where instead everything localizes within a story, with the piers of that story getting damaged in shear or in bending. Now, ideally, we would like to have the first mechanism, because we can spread damage and deformation demand throughout the building height, but in many cases with masonry structures, we observe sub-story mechanisms. If we are lucky, we can obtain what we have on the right-hand side of the slide, where the building located in Amatrice suffered the 2016 August earthquake, and you can see that there all elements, all piers and all spandrels are damaged in their planes. The building had improved connections between intersecting walls, between walls and floors. In that case, we can observe the result of a global response where all elements were exploited with their full capacities. Now, when buildings are responding in a global way, and when walls then are excited in their planes, we may have mainly three types of failure modes. First of all, the first of them is bending, so a flexural mechanism, which may lead to toe crushing. We may have sliding at the over a flexural crack, typically at the base or at the top of a pier element, or we may develop diagonal shear cracks that may go through the bed joints, or they may also involve elements, especially if we talk about weak blocks or stone masonry. Now, the techniques, the strengthening techniques that we will see today are mainly aimed at improving both performances, the out-of-plane arching mechanism and the in-plane shear and flexural capacities. Now, to improve masonry quality and strength, we have some more traditional techniques which typically tend to restore or improve the masonry quality by replacing part of the materials. For example, you may have joint repointing, where part of the mortar joints are removed for about 5 centimeters or so in depth, and they are replaced with new, more performing mortars. Have grout injections. These are aimed at filling the voids that we may have within the loose filling between masonry leaves. Other techniques are aimed instead at fixing cracks, pre-existing cracks in our walls. One of them is masonry stitching. In this case, we remove the damaged portion of the masonry and we replace it with new masonry, of course, intact with no cracks. Or another solution might be to adopt a reinforced repointing method, where the joint repointing is associated with the insertion of steel bars, helicoidal bars, materials that can resist tension and that can bridge the existing crack. Or we may aim at improving the tensile strength of the masonry material just by adding reinforcement within slots, like in the top right photo. In that case, the intervention is the insertion of vertical reinforcing elements. It can be steel or composite bars or plates. And also we may want to connect together the masonry leaves throughout the thickness of the wall. In this case, there are several techniques that can be adopted. The one I'm showing here is called reinforced injection with grouted post-tension ties, for example. This is a possible solution for this problem. But what we are going to focus today are other methods that are based on adding material overlays. Now, traditionally, we have the adoption of reinforced plaster. This has been used in Italy, at least quite extensively in some regions, especially in central Italy, starting from the 70s, I would say. And also in the 90s or so, another technique became popular, which was based on the application of the fiber reinforced polymers, or FRPs. Now, these techniques have evolved in the 3 that we see at the bottom, and they are the use of composite meshes instead of steel meshes for the reinforced plaster, and this technique is called composite reinforced mortars. We have also fabric reinforced cementitious matrices, or FRCM. This is the evolution of FRP overlays. And finally, we have a technique that is based on timber material, again connected to the masonry surface, which we will see in today's presentation acts very similarly, from a certain point of view, to the CRM or the FRCM strengthening method. So let's begin talking about CRM and FRCM strengthening. With CRM, or composite reinforced mortar, we mean a strengthening technique which has a thickness greater than 30 millimeters, as opposed to the FRCM materials, which have a thickness less than or equal to 30 millimeters. So this is one of the main differences between these two types of interventions. CRM, as I was saying, is an evolution of the traditional reinforced plaster, because we are replacing the steel welded wire mesh with FRP, oftentimes GFRP mesh, but could be also a carbon FRP or aramidic FRP mesh. What is the advantage in doing so? Well, steel typically has problems with durability, which requires great thickness to protect the steel reinforcement from corrosion. When we use an FRP mesh, instead we can reduce this thickness because we don't have this corrosion problem. On the other hand, FRCMs are the evolution of FRPs. Now, in this case, one problem with the adoption of FRP is the lack of compatibility, material, chemical compatibility between the epoxy resins that are used to form the FRP and the old masonry layer where this material is applied. Now, by replacing the polymeric matrix, the epoxy matrix, with cementitious or in some cases hydraulic lime mortar, we can achieve a better compatibility between the new and the old materials. In both cases, the intervention can improve the out-of-plane response of these walls, especially against vertical arching, thanks to the vertical fibers or yarns or bar, if we talk about composite mesh. They also improve the in-plane response of the masonry elements. If we look at a pier, the vertical fibers or bars can improve the flexural response of the element, provided they are anchored top and bottom into the nodal regions or to the floors and foundation. But the horizontal components of the mesh or of the textile will provide strength against shear. So we can improve both types of response in the plane of the element. So we can basically say that adding a CRM or an FRCM overlay to a masonry element is like adding an external reinforcement, as these materials have tensile strength. So it's like adding external reinforcement to the existing unreinforced masonry. Now, here at the University of Pavia, we have performed a quite extensive campaign on the strengthening of stone masonry with both CRM and FRCM solutions. We have performed a lot of diagonal compression tests on bare stone masonry and on a number of 33 jacketed wallets, where we employed basically 11 different combinations of materials to form CRM or FRCM. And this allowed us to investigate the increment in the masonry tensile strength, or in an equivalent, let's say, masonry tensile strength due to the strengthening system. Now, this is quite a simplified approach to treat the problem, because in reality, it's not simply increasing the tensile strength of masonry, it's like adding reinforcement, as I was saying. But there are design guidelines in the Italian code and in the upcoming edition of the Eurocode 8 Part 3, where we can treat this intervention like an increment in the tensile strength of the masonry with a magnifying factor. Then we performed a cyclic shear compression test on 2 jacketed piers, and in this case we wanted to investigate actually how, not the strength of the material, the masonry material, but how the lateral strength of the element was increasing thanks to this intervention, and especially how much the lateral displacement capacity was affected by the intervention. As I said, we investigated these interventions when applied to stone masonry walls with a thickness of 300 millimeters, quite weak masonry. These walls were made of two independent leaves, poorly interconnected without through stones, and with a filling between the leaves made of a mix of mortar and stone scraps. Then we characterized our masonry material using vertical compression test and diagonal compression test in order to find out, first of all, the strength and the elastic constants for the bare material, as listed here in this table. So then we can express the equivalent increment of tensile strength from the diagonal compression test with a reference to this FT0 of 0.14 megapascals of tensile strength of the bare stone masonry. So, diagonal compression tests were performed on 1 by 1 meter square specimens loaded over compression along a diagonal, and were able to record the maximum force resisted by the specimens. The type of strengthening that was adopted was either CRM or FRCM. For CRM systems, we had 9 different combinations using several types of mortars, of GFRP mesh, and connector type and distribution. I'm not going to list all of them, but we try to investigate the effect of these different parameters. For the FRCM systems, we had 2 combinations, basically one using perimetral strips of monodirectional textile, the other one using bidirectional textile applied to the entire surface of the wallet. And this is what you obtain. So here you can see how we determine the tensile strength, basically considering more circles, and starting from the applied load P, we're able to define the principal tensile stress, and when P reached its maximum value, that principal stress was the tensile strength of the material. And we can see that with the different CRM methods, we reached tensile strength increments ranging between 2.3 and 3.3. So on average, we can say a 2.8 factor or so. With the FRCM solutions, this increment was a little bit less. We talk about values between 1.9 and 2.4, so let's say 2.2 times. This is, as I was saying, a simplified way of approaching the problem. If we want to get more information on the effect of these strengthening techniques on masonry elements, not just on masonry materials, we need to follow a different path. We need to perform in plane tests, shear compression. In this case, the tests were cyclic, and the forces were applied quasi-statically, meaning that we didn't have any significant dynamic effect. This is the test setup. Basically, our specimen was loaded with 3 actuators, 2 vertical, 1 horizontal, to control the applied vertical force, to control the boundary condition at the top of the specimen with the vertical actuators, and with the horizontal actuator applying lateral cycles of force and displacement. The specimens included, for both cases of CRM and FRCM strengthening, 1.2 by 1.5 meter pier, and also portions of the top and bottom spandrels, because we wanted to be able to anchor the CRM and the FRCM materials within the nodal regions between the pier and the spandrels, so to exploit them and explore their effect also on the flexural response of the pier. The masonry was the same as investigated with the diagonal compression tests, same mortar, same stones, and same thickness of 300 millimeters. So, for the CRM solution, one of the different combinations investigated with the diagonal compression test was chosen. A hydraulic line mortar of M15 class was selected. The mesh was a rectangular GFRP mesh with a weight of 400 grams per square meter, and helicoidal connectors were adopted to connect the strengthening to the masonry substrate. And this is important to know, we'll see in a while. The pier was strengthened with 8 connectors. So this dense distribution was probably important for the success of this strengthening. In the case of the FRCM, which was applied to specimen P2, we used a cement-based M20 class mortar reinforced with glass fibers, and we adopted the bidirectional textile, which had a weight of 22 grams per square meter of PBO, which is a synthetic fiber, in each direction. And in this case, the connectors were also made of PBO, as shown here in the figure. You can see the end of the connector applied and spread it onto the surface of the FRCM, where it's bonded with a mortar. Now, in this case, the distribution of connectors was less dense. Over the pier, we had only 5 connectors. And this may be the cause of the a little bit less satisfactory performance of this strengthening compared to the CRM for this specific testing campaign. Now, we kept constant the axial force to reach at the base of the pier 25% of the masonry axial strength. We tested our specimens in double curvature conditions, meaning that the top spandrel was not allowed to rotate while it was displacing laterally, and we applied lateral forces and displacement in cycles of 3 per increment. And these are the lateral force displacement responses that we obtained for the 2 specimens, for the CRM strengthened specimen P1 and FRCM strengthened specimen P2. Now, in the case of the CRM strengthening, we had a response governed by flexure all the way to the end of the test with extensive toe crushing at the corners of the pier, while with the FRCM, the failure of the specimen was controlled by diagonal shear cracking. So with the CRM system, we were able to increase by a factor of 1.5 the lateral shear strength of the element, compared to what we expected for the same pier without any strengthening system, while the ultimate drift ratio, that is the lateral displacement divided by the height of the pier, 1.5 meters, was like 2.5% when the strength dropped by 20%. This is more than 3 times the limit that we find in EC8 for unreinforced masonry, that is 0.8%. Instead, for specimen P2, where we applied the FRCM strengthening, I said failure was controlled by diagonal shear failure. This happened likely because the FRCM layers detached from the masonry surface. And this is why I was saying maybe having here only 5 connectors as opposed to the 8 connectors for the CRM, maybe this led to this type of failure. So the jacket detached from the surface of the masonry, and at this point the masonry failed in shear, in diagonal shear. In any case, the strength increment compared to the predicted strength of the unreinforced masonry pier was 1.4 times, so almost the same as we obtained with the CRM. You can see this. And in this case, the ultimate drift ratio, again at a 20% strength drop, was 1.5%. So it's actually 4 times the limit that we would find in EC8 for an unreinforced masonry pier failing in shear. For this case, the Eurocode gives a limit of 0.4%. Now, in both cases, again, we can say that the response was like the one of reinforced masonry elements, both in terms of strength and displacement capacity, provided that detachment of the strengthening system is prevented, especially for the flexural response. Now, this is what happens when connection between the strengthening and the masonry substrate fails. You can see on the left-hand side the case of a wallet subjected to diagonal compression with only one through connector in the center of the panel. You can see that we have separation of the masonry leaves, which are not held together by the connectors. On the right-hand side, we see what happened to pier P2, the one strengthened with FRCM, because of the not so dense distribution of connectors. You can see buckling and detachment of the FRCM layer here. And after this happened, well, at the end of the test, we removed completely the FRCM and we exposed the masonry pier. You can see diagonal cracks, which are definitely telling us that the pier failed in diagonal shear. So again, connecting the strengthening to the masonry is, of course, of very, very big importance. So let's move now to the timber strengthening. Now, the solution that we have developed here at the University of Pavia and at Hughes Center Foundation is based on the application of a timber frame to one side of the masonry wall, then to nail oriented strand board or OSB panels to this timber frame, and again of important, very big importance, connecting all this retrofitting system to the masonry by mechanical connections. In what we will say next, the most important connections are the ones at the base and at the top of the pier, the ones that you can see here and here. These are the tie-down connections, labeled also C1, and these basically provide continuity between the vertical timber posts and the floors of the structure, allowing to develop a flexural contribution from the strengthening system. Without this type of connection, we wouldn't be able to take advantage of the retrofit in terms of flexural strength, because we wouldn't have continuity at the top and at the base of the pier. Now, as with CRM and FRCM systems, also with this timber retrofit, we can increase the out-of-plane capacity of the walls. In this case, we can just take advantage of the post as simply supported beams, pinned at the top and at the bottom, and with their flexural strength, they can just resist the inertial load coming from the masonry, which can be considered just as a weight without considering its contribution to the strength. Instead, what concerns the in-plane response of the retrofit, in this case, it's very important, as I was saying, to considering the effect of the connection between the vertical posts and the top and bottom floors or the foundation, in order to take advantage of the flexural contribution of the retrofit. while the nailed OSB sheathing can be considered effective in adding a component to the shear resistance. In this case, the experimental campaign included cyclic shear compression test on one bare and one retrofitted piers, and two dynamic shake table tests, one on a bare masonry building, the other one on the same building with the same geometry and same characteristic, but strengthened. In this case, the masonry was a calcium silicate brick masonry with a cement mortar. This is typically found in Northern Europe. And the masonry was a single leaf with very, very thin walls, only 10 centimeters. And as before, the masonry was characterized with appropriate material tests in order to obtain its compressive, tensile, and shear strength properties, as well as the elastic constant. I mean, in this case, let's look directly at the cyclic shear compression test on piers. The setup is very similar, but in this case, we didn't have spandrels connected to the pier. We just looked at the connection between the pier and the what would be a foundation and a top floor, just by connecting it to the footing and to the top reinforced concrete beam, which are part of the testing setup. You can see here how thin, how slender was this pier, only 10 centimeters thick and 2.7 meters high. And these same dimensions apply to the bare and to the retrofitted specimens. The posts and nogging of the strengthening system were made of red solid FIR, while OSB panels of category OSB 3 were applied to the frame and nailed to it. The tie-down connections had a characteristic tensile strength of 11.6 kilonewtons. Again, these are very important in order to obtain a contribution to the flexural strength. In this case, the axial load applied to the system was able to reach 5.4% of the masonry compressive strength. Double curvature boundary conditions were also considered, and a similar protocol in terms of lateral force displacement cycles was followed as seen before. And here we can see the response of the bare URM pier and the retrofitted pier. Now, in the case of the unreinforced element, we developed a sliding shear mechanism which led to the failure of the specimen, while when we applied the timber retrofit, the failure mode was mainly related to toe crashing, and only at the very end of the test we developed diagonal cracks, probably also due to the reduced section because of toe crashing, over which all forces were transferred. And what we can see is that with the retrofit system, we increased the lateral strength by about a factor of 1.35. So the reinforced, the strengthened specimen was 35% stronger than the unretrofitted one. Again, we changed the failure mode. We didn't allow shear sliding to happen because all the mechanical connections, which are part of the retrofit solution, and instead we develop a toe crashing mechanism followed by diagonal shear cracking, reaching an ultimate drift ratio at 20% strength drop of 2%, as opposed to the 0.75% of the unreinforced masonry pier. This means that the displacement capacity was 2.67 times the one of the bare specimen, which is a huge increment. Again, as with the other two retrofit techniques, we can say that our retrofitted pier behaves more or less like a reinforced masonry element, provided that mechanical connections are actually working and connecting the retrofit to the pier and to the rest of the masonry structure. An important aspect here is that the timber frame can also help the masonry in carrying vertical loads when the masonry is significantly damaged, for example, upon toe crashing. And here we can see at the top what happened to the unreinforced masonry specimen, and the bottom, what happened to the strengthened specimen at different lateral drift ratios. So basically, you see they're vertically aligned in terms of equal or nearly equal lateral drift ratios. You can see that the retrofitted pier developed significant toe crashing with loss of masonry. And this is why I'm saying it's important to connect well the masonry to the timber. For example, if you provide more connectors between the post and the masonry at the edges of the element, we can avoid the loss of that masonry. But in any case, the timber frame was able to resist the vertical loads that were not taken anymore by the masonry. Now you can see that 2% drift ratio is at the very end of the test. You see the section here is significantly reduced, almost to half the initial one, and probably this is what induced this cracking here, where kind of the masonry was basically falling apart, with these diagonal cracks that might be related to the transfer of shear along this diagonal. Important is also to see what happened at the tie-down connections. Here at the base, you can see this buckled L-shaped connector. This is the response of the connector in its elongation, so the vertical displacement, local vertical displacement here measured by this potentiometer against the horizontal displacement. You can see that this region, this element, is shortening progressively as we go on with the test. This shortening is related also to the loss of masonry in this region and the fact that all this timber is carrying the load and is basically punching through the bottom sill plate here, and this connector is buckling because of this imposed axial compressive deformation. We also performed, as I was saying, dynamic shake table test on two buildings, identical geometries, identical materials, one just unreinforced masonry, the other one with the retrofit applied and combined with diaphragm strengthening. So the building had a timber diaphragm at the second floor, and that was also stiffened with OSB panels. Now let's compare their response at the same level of shaking intensity. The ground motion that was chosen was compatible with what is expected in the Netherlands region of Groningen, where they have a problem with induced seismicity due to gas extraction. So it's not a long natural earthquake. It's a very short earthquake, but for this type of construction may cause some damage. Now, here we went to 133% of the intensity associated with a 2,500 years return period. And I will show you now the video. We can see that the unretrofitted building is quite damaged in this region. We have sliding here at the top, cracking here at the bottom of the second story, where all the damage is concentrated. While under the same shaking intensity, the retrofitted building is basically moving all together. Nothing is actually happened, just small displacements, but no concentrated mechanism, no localized mechanisms, no localized damage. And we were able to push the retrofitted specimen to twice as much the intensity, and here you can see that most of the damage was related to the loss of this window here that fell down. Actually, the interior leaf of the masonry, which is the load-bearing one, was quite damaged at some point, but in any case, the building was able to develop a global mechanism taking advantage of the masonry strength. It damaged the piers at the ground floor of this building. Now, to conclude this presentation, I just want to show you some analogies between these three strengthening systems. Why that? Well, there are some guidelines that are published by the National Research Council of Italy. They're published also in English, and they can be used as a reference for the design of FRCM strengthening. We don't have at the moment design guidelines for CRM and for the timber system, but I will show you that these systems behave similarly to each other, and so we can take advantage of an analogy to find equivalent parameters for an equivalent FRCM system that will represent somehow either the CRM or the timber retrofit. This can also be used if you want to implement this kind of retrofit in softwares. For example, Tremuri offers the possibility of including an FRCM retrofit in the building. And taking advantage of this analogy, you can actually define an equivalent FRCM that you can introduce in the model, so to see, or at least have an idea of the more or less evident effect of the retrofit that you would like to design. So you can see that the axial flexural strength enhancement is due to the vertical fibers, highlighted here in red, in the FRCM system, or the vertical bars of the composite mesh of the CRM retrofit, or by the tie-down connections C1 of the timber system. Again, remember that in the timber system, the strength of the vertical post is actually limited at the connection level by the C1 connection, which is usually weaker than the post. So that's controlling, as they are in series, that controls the force that can go into the post due to flexure. For shear, instead, the horizontal fibers here in blue of the FRCM are contributing, as well as the horizontal bars of the composite mesh in the CRM system and the nailed OSB layer of the timber retrofit. So we can set up analogies between these components, again, to transform one into the other one and be able to follow either the design guidelines or to implement these solutions in a numerical model. Again, I will make reference to this document, the CNR DT 215-2018 of the National Research Council of Italy, which addresses the design of FRCM retrofit. There are some parameters required in the equations. They are nothing but the equations of the flexural contribution of a distributed reinforcement, but be careful, a brittle reinforcement that cannot plasticize, and the equations of an additional shear contribution for what concerns the lateral shear resistance. Now, you can see this parameter BF here is the width of the strengthening of the pier. For the analogy, we can just say that BF is equal to the overall width of the element, which is H. So we can just set this. There are some coefficients, alpha T and F, that we can just take equal to 1 for our analogy, doesn't matter. And we can also select an arbitrary value for this thickness, T2F. This is the overall equivalent thickness of the FRCM strengthening. Now, we are trying to find equivalent properties, so whatever value we adopt for this is going to be fine, because all other parameters will depend on our choice for this value. Now, the first equivalence that we consider is the one between the axial rigidity of the vertical fibers of the FRCM and the one of the vertical bars of the CRM or the C1 connections of the timber retrofit. By setting up this equivalence, we can find these equations here. So the value of the elastic modulus of the equivalent FRCM fibers that we have to consider is based on the actual elastic modulus of the composite mesh or of the steel used for the connectors, and depends on the overall areas, of course, either of the mesh for CRM or overall area of all the connectors at one interface for our timber system. The other equivalence that we need to consider is the one between the total axial strength provided by the vertical fibers of the FRCM and the one of the vertical bars of the CRM or the tie-down connectors of the timber retrofit. Since we have already set up this first equivalence that led us to the value of EF, and we have fixed other parameters, T2F and H, basically, this translates into equating the design ultimate tensile strain of the FRCM fibers to the one of the mesh for the CRM or the one of the steel for the connectors in the timber solution. And this is what concerns the flexural strength. Now, moving to the shear strength, all these three solutions are basically adding a shear strength contribution to the original shear strength of the URM pier. So simply, we equate the value of our additional shear strength calculated for whatever solution we have chosen to the one that is given in this CNR document for the FRCM retrofit, and we can find this equivalent parameter, NF T2F. This is basically the overall equivalent thickness of the CRM effective in shear. So again, by doing this, we can just transform again our CRM or timber retrofit into an equivalent FRCM strengthening solution. And by doing this, again, we can take advantage of these guidelines, as at the moment we don't have guidelines specific for CRM and for the timber retrofit. And also we can take advantage of modeling techniques that are already available, for example, in Tramuri, to model this FRCM or FRCM equivalent solution in our three-dimensional building model. Now, these are some references for what I've presented today. And with this, I've concluded my presentation. I hope you have enjoyed it.